Alright you guys, this is video E3.4-3 notes how we measure earthquakes. So we're going to look at some of the scales that are used to measure earthquakes. You might be surprised that it's not just the Richter scale, and that is not the most accurate one. The learning target here is a new one. We got E3.4b. Describe how the sizes of earthquakes and volcanoes are measured or characterized. So this set of notes will focus just on earthquakes, and then I have a lab called Kaboom. It's actually, I don't know if it's that spectacular, but anyways, that one will look at volcanic eruptions. Okay, so this is just how we're measuring earthquakes. So you should be looking at this sheet right here, and we'll go ahead and get started. Alrighty, so there are three scales to measure earthquakes. First, the Richter scale. That's the one that we always hear about. This is the one that the media always uses to let us know, or let the public know, the general, I guess, size of an earthquake, or maybe I'll say magnitude. The other scale that is used is moment magnitude scale. And we'll look at the differences and similarities here in a minute, but the moment magnitude scale is the one really used by scientists. It's more accurate, especially with our bigger earthquakes. Okay? And then finally, the modified Mercalli scale. It's not really measuring magnitude, but the modified Mercalli scale is different because it is looking at the damage done, things that you and I would see, observations we would make to determine how large maybe an earthquake was. Okay? So the Richter scale, our familiar one. It assigns a single number to quantify the energy contained in an earthquake. So we're measuring the amount of energy released from that earthquake. The magnitude is based on how fast the ground moves at a seismic station. Okay, so remember, seismic stations are picking up all the waves, the primary wave, the secondary wave, the surface wave. And our Richter scale is measuring the actual ground movement at those stations. So basically we're taking our data from a seismograph and determining the Richter scale from that, a Richter scale reading from that. So on a Richter scale, it says the magnitude is a base 10 logarithmic scale obtained by calculating the logarithm of the amplitude of the waves measured on the seismograph. In other words, look at my example here, because base 10 logarithm scale, that sounded kind of confusing. So an earthquake that measures a 5.0 on the Richter scale has a shaking amplitude, and we're measuring the waves on the seismograph here, 10 times larger than that of a 4.0 earthquake. Okay, so the amplitude, the shaking amplitude is 10 times larger. And that's why we see our scale 1, 2, 3, 4, and so on. Okay, largest earthquake recorded is what, a 9.5 or a 9.6, which is enormous. But the interesting thing here is that as you go from, say, a 4 to a 5 on the Richter scale, you are measuring that the shaking amplitude is 10 times larger. That's that base 10 logarithmic scale we're talking about. But as you go from 4 to 5, it's actually a release of about 31.6 times more energy. Okay, so the 4 to the 5 is a 10 times larger shaking amplitude, but actually a release of 32 times more energy. Pretty incredible. So as we look at this Richter scale here, we can see what these different readings are telling us, and that earthquake is not really doing anything till about a 5 on the Richter scale, where damage is beginning. And then we have some of the more notable earthquakes here. Okay, these New Madrid ones are pretty interesting. They were like 8.2, 8.3, 8.4. That's in Missouri, right in the middle of that North American plate. And as you read historical accounts of that, they're pretty incredible, and that it actually changed the flow of the Mississippi River. The Alaska quake, largest in the United States, and then way out here, what's it say down here? There's about a 9.5 on the scale. Okay, so offshore of Chile, back in 1960. But again, it says the base 10 logarithmic system, increasing that shaking amplitude 10 times. But as we go from one number to the other, it is a 32 times more release of energy. So the next scale, the moment magnitude scale. Again, we're assigning a single number to quantify the energy contained in the earthquake, but the magnitude is based on something called the seismic moment. The seismic moment. And it says the moment, here in parentheses, whoop, is the area of the fault multiplied by how much the fault slipped in that event, that earthquake, and then the shear modulus of the surrounding rock. So it also takes into account the type of rock that is there and how that rock would break. Okay, you know, its strength, its hardness, things like that. So this seismic moment is a combination of things that is used to then assign a number or magnitude to an earthquake. It is similar to the Richter scale, but it has some differences. So as we're looking at this moment magnitude scale, we're still seeing it read as a 2, 3, 4, 5, 6, 7, 8, 10. And believe it or not, you guys, there's no upper limit. It doesn't stop at 10. It could go on 11, 12, 13, 14, you know, 15, 20, 25. That would be unfathomable, I think. But as we look at this and go up, you can see here, if I look at the very top of this guy, now we see all our earthquakes. And we see that Chile earthquake way up here, this 9.5. That's pretty incredible. But if I go over here to this side, and we see way up here, very top, it says 10 to the 31, a meteorite impact. So about a 6-mile, 10-kilometer diameter, 6-mile diameter meteorite moving at 20 kilometers per second. What's that work out to be? 12 miles per second velocity. Come down here. That's somewhere around an 11 or 12, the way that would shake the Earth as it made impact. So that's pretty incredible. But it's also neat to look at this and see world's largest nuclear explosion is right about here, and that's below these huge earthquakes. Okay, so it's somewhere between an 8 and a 9 on that Richter scale. We're shortly here going to study the Mount St. Helens eruption and the force that had on the shaking of the ground, and that is still below these really large earthquakes. Okay, and even looking at you know, the average tornado, a lightning bolt, typical thunderstorm, the bombs we dropped on Hiroshima would have had like a 5.0, so a very minor earthquake. But we all know the destruction atomic weapons can do. So this is a different scale. The similarities between them, there's no actual maximum value. I did just say that. And an increase in one whole number equals an increase in about 32 times more energy released. That is the same between them. Or use that pause button if you got to. So the difference is, the Richter scale is a mathematical evaluation of wave amplitude. Remember, it's that base 10 system, so we're measuring wave amplitude for the Richter scale. The moment magnitude scale is a mathematical evaluation of the amount of displacement or movement across that fault. Okay, so we're taking into account more factors to come up with this number or assessment of a scale for the moment magnitude. And I have down here several stars. The moment magnitude scale is more accurate for medium to large earthquakes and is used by scientists. This is what scientists are using, not the Richter scale. The Richter scale was devised in the 30s, and the moment magnitude scale was devised decades later to sort of replace the Richter scale. Okay, the Richter scale is really just used by journalists I guess to tell a story, because it's what we're familiar with, we know about it. If they started saying the moment magnitude, you know, whatever, it was a 9 on the moment magnitude scale, people would be confused. And when we're talking about an earthquake at this day and age, we really just want to know the facts. And when they say Richter scale, that's something that the public understands. So lastly, we have the modified Mercalli scale. And this classifies earthquakes, as I said, by their effects. What we observe has happened, the damage we see happening. So the energy and effects are not necessarily strongly correlated. Okay, so the modified Mercalli scale is not a scale necessarily that would report to the public. It doesn't give us an idea necessarily of exactly how strong it is, because it all depends on a variety of characteristics. It says a shallow earthquake in a very populated area with soil of certain types can be far more intense than a much more energetic deep earthquake in an isolated area. In other words, it depends on the soil type, how populated an area is, if that area has built their buildings to be earthquake resistant, not proof, but earthquake resistant. So lots of things go into play here. If we moved buildings from like Southern California here to Michigan, and we somehow had a huge earthquake, they would fare much better than our current buildings. We do not build to resist earthquakes. We don't have to. It's very expensive to do. And the chance of us having a large earthquake, maybe from that New Madrid fault, are probably not enough to make us even consider building like that. And so here is a picture of the modified Mercalli scale. Now, we've imposed it here with this Richter magnitude scale to see kind of what would be happening at those points on the Richter scale, but you can see here the modified Mercalli scale is based in Roman numerals. We have 1 through 12 here, and we are just talking about some of the things that could happen. I believe on the maps you look at in our area in Michigan, even if there was a very large earthquake at the New Madrid fault in Missouri, which is pretty far south of here, it says we'd be about a 4. Felt indoors by many, outdoors by a few. Some might be woken up at night. Dishes, windows, doors would be disturbed. Cars would rock on their shocks. You might see a hanging chandelier swing a little bit, things like that. Okay. But again, the modified Mercalli scale is based on effects, observations, not a mathematical representation of the amount of energy released. Okay. And that's all.